All right, welcome everyone. Today is day 3 of build. Hopefully you guys didn't party too hard last night. We're going to be talking about something we're very passionate about, building mission-critical multi-tenant applications with Cosmos DB. My name is Andrew Liu. I'm a PM on the Cosmos DB team.
I'm Mark Brown. I'm a PM also on the Cosmos DB team.
And I'm Terry Duchatel. I'm from Citrix Systems.
Awesome. So today, what we're going to do is we're going to talk about a pretty common scenario for us, which is multi-tenant apps. And when you look at multi-tenant applications, typically there's going to be 3 high-level core concepts that you really want to get right. The 3 concepts are going to be, how do you handle performance isolation and manage that with respect to costs? The second is going to be if you have a global user base, as well as if you want high availability. When you use things like global replication, how do you manage the trade-offs between consistency, availability, as well as latency? And of course, the third aspect is going to be around security. How do you make sure that you can manage things like least privilege principles so that you can have good security isolation? And we're going to talk about this in the context of a token broker, which we've deployed live. And Terry Duchatel is going to give you an awesome view on how Citrix handles this with Cosmos DB. So I assume everyone here has familiarity with Cosmos DB already. If not, I'm going to just quickly level set. I'm not going to spend more than a minute on this. The short gist here is this is a distributed database. We focus on a lot of core tenets around partitioning, replication, and resource governance. And everyone on my team likes to call this like our building the house diagram. Basically, the partitioning, replication, and resource governance gives us a set of core capabilities around turnkey global distribution, elastic scale-out of storage and throughput, guaranteed low latency, a tunable consistency model backed by comprehensive SLAs. This is our back-end platform. We can express various different data models on top of this back end, including the key value, column family, document, and graph data models. And these get made available through a variety of different APIs, including our own core SQL API, as well as a bunch of open source-based API, including Tables, Cassandra, MongoDB, and Gremlin, and then with our newly announced etcd API for Kubernetes clusters, as well as a Spark API for doing hybrid transactional analytical processing. Now, let's jump into the first concept. Performance isolation. How do we want to think about how do we isolate the performance across each of our tenants? And we manage that in a cost-effective manner so that we don't have noisy neighbor problems. Now, to begin with this, if you haven't looked at noisy neighbor problems before, I'm going to begin with a simple analogy. And where have we seen noisy neighbors before? Has anyone here had a roommate before? Hey, yeah, like most of us have had housed with roommates before, right? So to make an analogy, I have a house here. It's $1 million house. If I have a single tenant within that house, well, I'm going to have to tell this tenant, you know what? The costs $1 million. There's only one tenant to spread it around, $1 million for that tenant. And of course, the intuitive thing is, hey, I can increase the number of tenants to spread that cost across tenants. And so if I were to, let's say, double the number of tenants, I can decrease the cost per tenant by half. And you know what? This is going to be a really fun, rowdy house. We're going to pack 1,000 tenants in here. And that way we can really floor the cost per tenant. But the challenge here is the noisy neighbor problem. What if Carol really loves, I don't know, just poor music taste? We have thin walls in this house. And she's blaring music, and Alice and Bob and the 900 other tenants not so happy. So how do we think about isolating these? Well, one model of isolating these is to put them each in a different house. If I have 1,000 tenants, put them in 1,000 houses. But I'm back at the problem of, wow, it really got costly per tenant. And so today what we're going to talk a little bit about is all the various knobs and levers you have to manage this performance isolation still in a cost-effective manner. It turns out that when you're looking at servers, not too different from housing. Now that we're all ready to become landlords, who's ready to become a landlord? Wow, I'm surprised if people raise their hand for that. Okay, let's go into real estate. What we're going to talk about here is servers. It turns out when you build multi-tenant servers, same thing. If you have, let's say, 1,000 tenants packed on the same box, one tenant runs an extremely expensive workload, uses a lot of CPU, a lot of memory. How do you make sure that that doesn't degrade the performance of your application for all of your other tenants? And if you're going to go and break it down to a server per tenant, you're back at this, wow, this got really costly really fast. So some background context regarding Cosmos DB. How do we apply this to Cosmos DB? For the folks who haven't looked at Cosmos DB before, very quick level set again. When you provision a Cosmos DB account, we have this resource model that we start with a database account. That's the instance that you connect with. Underneath that, we can provision a set of databases, and underneath that, a set of containers. Explaining containers real quick, for those who have played with Cosmos DB, a lot of times you'll see the word collection, you'll see the word table, you'll see the word graph. Because we support different data models, when you're talking to, let's say, a document-oriented API, we like to call this a collection. When you're talking to one of our graph APIs, we like to call this a graph. I'm using the word container not in the form of like a Docker container, but rather as just a data model agnostic way of referring a thing that contains a bunch of data. And underneath that, we actually store our actual data, whether that is a document, a row, a node, or an edge, and I typically refer to these as items. Now, what Cosmos DB does is once you have this container, think of this as a bag of items, you're going to set up a partition key, and underneath the hood, what we have here is a distributed system. What we're going to do is we're going to set up different partition sets, which are composed of physical partitions, which are then composed of replicas. We're going to talk a little bit about the trade-offs between consistency, latency, and availability in a little bit later in this talk. But the gist here is we're going to set up one of these replica sets per region, per partition set. But then you're also going to want to think about how do I actually partition my tenants across this model. The other key thing to understand about Cosmos DB, if you haven't looked at this before, is how we model the physical resources for doing compute whenever a request comes in. And so if you have multiple dimensions like CPU, memory, and I/O, what we do is we normalize this into a single logical currency called a request unit, where we baseline a request unit as the machine cost of running a single point read on a 1 kilobyte record. And then everything is proportional from there based off of the request. So if we charge 2 RUs, it's basically a request that costs 2x the cost of doing a point read of a 1 KB record. Now, when we look at RUs, what you'll find very quickly is we have multiple ways of provisioning these RUs. We can provision the RUs at a database level, as well as we can provision the RUs at a collection level or a container level. When you're looking at a database level, what's really happening is we're provisioning a cluster of machines, and all of these different containers are going to be co-located on that same set of physical partitions. They're sharing the same set of resources. There's some benefits for doing so. There's also some trade-offs for getting this benefit. In contrast, when you do container-level RUs, what you'll see is the mapping from container and its logical partitions to physical partitions is going to be isolated. We're going to be able to have independent RU knobs on each one of these containers, and they're going to scale independently of all of the other containers, as well as not be able to tap into the same set of resources. Now, here are the different options that you can look at when building a multi-tenant app, ranging from left to right. What we have here is a few options we have are storing a tenant per database account, or sorry, a database account per tenant, provisioning a container with dedicated throughput per tenant, a container with shared throughput per tenant, and a partition key per tenant. What you'll find here is as you move from left to right, basically what you want to do is t-shirt size your tenants, because on the left-hand side we have increased isolation, but at the same time increased costs. At the far right side, we're going to have much lower amount of isolation, but we're also going to see much lower cost per tenant. And depending on the size of tenants and your scenario, you might actually even find like there are nice shades of gray in between. So I'm going to go from the lowest cost over to the greatest cost. Sorry, I'm going to read from right to left. But from a partition key per tenant, basically what you're doing is you're completely decoupling all of the physical infrastructure to a tenant. And the nice thing about that is that from a cost per tenant perspective, there is no cost per tenant. And if you have extremely small tenants where you need to build an extremely cost-effective solution, especially if it's like a B2C application, if you're building something akin to, let's say, Facebook, Well, if you're building a social media application, even a cost of, let's say, $1 per tenant, probably not palatable. Your margins are going to be very thin on a per tenant basis. In contrast, in the far extreme, if you're building something like, let's say, a cloud service and you're onboarding a B2B enterprises onto your platform, the cost per tenant, because they are also paying you a lot more for guarantees around performance of your system, you have a lot more wiggle room in terms of how you want to isolate them. Now, from a partition key per tenant perspective, some of the benefits here is because your tenants are sharing the same infrastructure, beyond cost, they're also sharing the throughput. And so if you have spiky tenants in which a tenant might spike at any given moment, but not at any same moment, all tenants will spike. This is like an analogy is like the banking problem. You don't need to be able to have enough cash on hand for everyone to withdraw their money, because honestly, you're not gonna have your entire customer base all bail out at once. But you need to be able to have enough cash on hand so that given a set of customers coming in, you need to be able to handle their transactions. Same thing here. What you're doing is if you have, let's say, 1 billion tenants, this is a wildly popular social media application, and at any given time you have 1 million users spiking, but you don't really want to provision for 1 billion users spiking. This is a pretty cost-effective way of sharing that throughput. Another side effect of this is because they're sharing the same container and they're co-located across, they're segmented by partition key. Because containers act as a natural boundary for queries, if you do have needs where you want to perform queries across multiple tenants, or even transactions across multiple tenants, depending on how you model your partition key, this gives you a mechanism for doing so because the container does act as that boundary for queries. You do want to think about the partition key a little bit different because that does become the natural boundary for a transaction. You can mitigate noisy neighbor problems. The nice thing is I'll talk a little bit how these partition keys get placed on the underlying physical infrastructure in just a second. But at a high level, you can also do things like grouping tenants by a set of containers such that, if I have tenants A and B on container 1 and tenants C and D on container 2, A and B cannot touch the resources for tenants C and D. Now, going from small to large, if we do containers with shared throughput, this gives you a bit more easy management of these tenants. You can conveniently drop a container whenever a tenant leaves, as opposed to having to do like bulk delete operations. And this also gives you a nice way of further mitigating that noisy neighbor blast radius on how you group your tenants. So example, you can group them by database as well. It gives you a lot of manageability aspects. And the big challenge here is as you strengthen that isolation, the minimum throughput for a database does scale with respect to the number of containers. We need at least 100 RUs to power each one of the containers when you're using the shared throughput model. And so this raises the cost per tenant to at least $6 a month per tenant, roughly. This is great when you're doing medium-sized tenants, if you're doing, let's say, a standard offer for B2B applications. And of course, as a B2B enterprise application, if you have, let's say, a standard SKU and a premium SKU, for the premium SKU, you might actually want to give them dedicated throughput. And so the analogy I like to make here is like, think of a VPS, a virtual private server, versus a virtual machine. You're going to have tenants who have, they want complete guarantees that no one else can tap into the resources provision for them. They want dedicated throughput, right? On a VPS, one tenant running an expensive workload is going to go interfere with every single other tenant on that same physical infrastructure. In contrast, when you do a dedicated model like a VM, you're actually setting aside these resources can be tapped in by one tenant and no other tenants. With containers with dedicated throughput, you're now given independent throughput knobs for each one of these containers, so you can scale each one of these tenants independently. And then you can also group these tenants within a database account based off of regional needs. The main difference between choosing containers with dedicated throughput and a database account per tenant is a database account is where we host all of the geo-replication knobs. And so if you do need different geo configurations, you can either do a database account per tenant, or you can do, let's say, this is a database account for my European tenants versus this is a database account for, let's say, my America plus EMEA tenants, just for sake of example. But as we go and strengthen this, what you'll notice here is the cost per tenant rises quite a bit more. And so what you want to do is you want to come up with a hybrid strategy where you're t-shirt sizing your tenants. A natural division is if you're building, let's say, a B2B application, if you have premium and standard offers, based off of whether it's a premium or standard offer, you can give them different levels of isolation. Another way to think about it is number of seats. So if you mostly cater, let's say, build an application for small to medium businesses, a lot of mom and pop shops, and then suddenly Megacorp comes in. And mom and pop shops, let's say, have, 10 users concurrently using your application at any given time, whereas Megacorp, instead of having 10 users, they have, let's say, 100,000 users. Well, there's also different ways of handling this, and if you were to go that partition key per tenant route, there's also different techniques you can apply, especially around salting a partition key. Keep in mind that our SDKs are intelligent enough to route a query based off of a set of partition key values. So if you were to salt, let's say Contoso is my Megacorp, and I were to salt that to Contoso 1, Contoso 2, I can actually allocate twice as much logical partition bandwidth on that particular larger tenant. In terms of resizing, if you have small tenants, let's say mom and pop is the next hot startup. They're really going gangbusters now, and they're much larger than what you had forecasted. How to perform tenant migrations, you're going to want to leverage our change feed to facilitate that online migration. Basically, the change feed gives you a nice mechanism of getting incremental reads from the database so that you don't have to have downtime of sucking one tenant out and moving them, but rather you can do online migrations, catch, let's say, another collection up when you're promoting them to dedicated throughput, and then once they're caught up, you can do a cutover. Now, to give you kind of a view of what happens behind the scenes, how we map these logical partition keys onto physical partition sets. We use a technique called consistent hashing. If you find what most literature will represent consistent hashing is a ring model. Basically, anytime you hash a partition key, you're going to be able to map that to a range of values from min value to max value, and that's going to wrap around. The key difference between consistent hashing and a naive hash is basically what you're doing is you're doing a range partition on top of the hash values. So let's say I have a model where I have partition set A and partition set B that needs to elastically grow. What you're doing is you're actually, based off of the hash of the partition key value, you're placing them somewhere on the ring, and that maps to either a physical partition set A or B. And from a consistent hashing perspective, what that allows you to do is subdivide partitions that are hot such that you don't need to do a complete rebalance, reshuffle of the world. Imagine if I did a naive hash, if I do a hash mod 2, and it's going 1, 2, 1, 2, 1, 2, if you map that to 1, 2, 3, 1, 2, 3, 1, 2, 3, what's going to happen is that's a big earthquake. You're going to shuffle the world. Consistent hashing gives you a convenient way of avoiding that, such that partitions can go and scale out independently. Now, looking at how this maps to our talk on multi-tenancy, imagine that if I did partition key per tenant, if I have, let's say, Alice, Bob, Carol as my tenants, but I also salt Megacorp, this is going to be Contoso. Contoso is a large company, and I break them up into, let's say, partition keys, Contoso 1, 2, and 3. What that allows me to do is that for hotter tenants, I can give them a bit more throughput than my small mom and pop shop. As you strengthen that to a database level offer and share the throughput across containers, you can also map that such that what happens behind the scenes is partition keys belonging to collection 1 and collection 2 are going to be co-located on the same physical infrastructure as such. And as you strengthen that further, if you were to do, let's say, a container per tenant with dedicated throughput or a database account per tenant, really what you're doing here is you're actually provisioning dedicated sets of physical hardware underneath for which we can scale out independently. With that said, this is one aspect of multi-tenancy, and the next aspect we want to talk about is how to guarantee high availability and manage the trade-offs associated.
Thanks, Andrew. About some of the fundamental concepts that are key to understanding how to build distributed applications, systems, and databases in the cloud. So there's 3 concepts I'm going to cover in this part of the talk, and those are consistency, latency, and availability. And whether you know it or not, each of these concepts is fundamentally tied to each other, and there are some real essential trade-offs and decisions you need to make when you're building applications. They're going to run in a distributed fashion. So before I get started, I want to do something. I want to define consistency here. So who recognizes consistency in this context? Right? Sure, everybody, right? We all grew up with this. But in fact, in a distributed system, this is actually not what we mean when we talk about consistency. In fact, consistency in a distributed system or a database means the uniformity of data between replicas that are separated by tens, hundreds, or even thousands of miles. So it's a different concept in terms of that type of what we mean in consistency in this context. So in 1998, a computer scientist named Eric Brewer published a paper that eventually became known as the CAP theorem. And what it did is it postulated that for any distributed data store or system, you can only get two out of the following three things. Consistency, so I always get the most recent write, or I get an error back. Availability, so every request I send to the system is going to give me a response, even if it's not the latest data. Or partition tolerance, and that is that the system continues to operate despite an arbitrary number of messages being dropped or delayed between the network, or on the network between the nodes. So simply put, CAP says that if a network goes down, I have two choices. I have to choose for availability for that system, or I have to choose for consistency. So I'll give you an example here. I just want to illustrate this. So in this example here, I'm going to choose availability for my system. So what happens is I write some data onto one of the nodes, and then it replicates to the other node there. So when the network is working fine, this is great, right? This is what we'd expect to happen. But what happens if the network's cut in a scenario where I want to choose availability over consistency between these different nodes? Well, if I write data to one of the nodes in there, and I read it from another node, I have to give up consistency. I can't physically replicate the data because they're no longer connected. I've got a partition between them. Let's choose consistency in this model. So in this model here, what happens is I write data, and then it replicates. That's fine, right? We're consistent. We're also available, but we don't have partition in between the nodes. If I cut the network between those two nodes now and write some more data, what happens? I get an error. I can't replicate the data. I can't remain consistent between those nodes in the application. So I have to trade one for the other here, right? I've chosen consistency. I must maintain consistency between all the nodes within that distributed application or data store. So if the network is cut and I have a partition, then I basically lose availability. So CAP theorem is great in describing what happens when there's a partition between the nodes. But it doesn't describe everything. So in 2010, there was an addition kind of, or an addendum to the CAP theorem, and that's called PACELC. And what PACELC says is essentially, in a partition, yes, you have to choose between availability and consistency. However, even when the network still works, you still have to make a choice between latency and consistency. So that's what this looks like if you have a decision tree here, right? So when I have a partition, CAP theorem says choose between availability, get some answer, may not be consistent, or I choose consistency. I'm always consistent, but I may not be available. When I don't have a partition, right, so everything is working fine, I still have to choose between that latency for that application and consistency. So let me illustrate this. So in this model here, I'm going to choose consistency between my two nodes. So write some data, fine, but if I'm choosing consistency here, I have to wait for that data to act and then come back, right? I can't do any other operations. I'm losing some latency, or I'm incurring some latency there while the data is being committed and replicated to all the nodes in the system. So here we go. I'll show that again. So let's choose latency. So in this model here, I'm optimizing for latency. I don't care if I'm consistent between the nodes. So if I write data, fine, and then read it, I may or may not see the same answer in all the different nodes there, right? The advantage there is I can blast as much data as I want into any of the nodes, but the result may not be consistent across the entire system. So let me go a little more into read latency. So there's two types of latency we want to talk about here. There's the read latency for the system, and then there's write latency. So let me go into the read latency. So to expand on latency, another way to think about this is performance, right? The lower your latency, the faster the requests from your client into your application to the database and back are going to perform. Within a distributed system, the way you do this is through replication, right? It's the concept of data locality. Get the data closer to your users. The further distance it has to travel, the faster the response times are going to be. In Cosmos, data replicated to your region is going to get less than 10 millisecond response times. And if you've used Cosmos, you can see how easy it is to add additional regions within your application. So I'm going to do some demos for you guys because I want to demonstrate this, what this actually looks like. Okay. You guys see that okay? Okay. Oh, actually, before I do that, let me set this demo up for you. So here's what I'm going to show you. I've got a couple of tests here, a couple of scenarios. In this one, I've got a company, and they have an application in a database located in East US. And they've decided they want to add a front end over on West US to improve the latency for their application for their customers on the other side of the country. I then have another scenario where they've decided, you know what, we want to actually replicate that database and put it behind the front end we've got in West US. So they've decided to deploy a replica over there. So got that set up. Now let me show you what this looks like. So here what I'm going to do is I'm going to test 100 reads against a single region account in East US from my front end in the West US. And what's that look like? It's pretty slow, right? So every request to get data has to travel all the way across the US to the database and then come back again. So I'm getting on average about 79 millisecond at the 99th percentile on that. Now, who wants to guess what this latency is going to be? Going to be fast? Slow? Worse? Super fast, right? So now you're going to get that low latency because the data is right up behind there, right? The distance it had to travel to get to that application is much less, or to the end client, right? So here you can see kind of the average latency between those two, you know, all the way across the US, about 79, 80 seconds of average latency versus 4 milliseconds, right? So your application, how is it going to feel? How is it going to respond? It's going to seem faster, right? Because that latency is going to be so much lower. All right, write latency. So in the preceding scenario, replicating data to the second region helped with the latency for the reads on this, but applications don't just read data, right? They write data too. So how do you deal with the write latency? Well, in September last year at Ignite, we launched Multi-Master. And what Multi-Master does, it makes every replica fully writable. So now, everywhere you deploy your replica, you can now use that as a master or a writable master, and then that data will replicate to every other node within the system. The nice thing here is, of course, in addition to the read latency you're going to get, which is going to be less than 10 millisecond, you're now going to get less than 10 millisecond write latency as well, and that's also covered by an SLA. In addition to that, you also get 5 nines availability on that replica as well. So let's show you an example of this. Okay. So here, I'm going to do 100 reads again from a single master in West US from West US. So as I showed before, super fast. My read latency is good because I've replicated to where that front end is going to ask for data. Now let's do 100 writes against that single master database that's going to go from West US over to East US. And as you'd expect, that latency is terrible. 75, 76, oh, there's one that bumped up over 100. So on average, 76 milliseconds for that latency. Now, we'll test 100 reads from a multi-master account, and of course, that's going to be fast. I'm replicated in that region, so that's an in-region request. Let's test 100 writes. Super fast, right? So now I've solved the problem of the write latency. I'm now going to get good performance, not just on the reads for the application, but any write that happens in every region I'm replicated into is going to be incredibly fast. And here you can see a summary of all the latencies in there. You know, within SLA, when you're using multi-master for writes in region versus something like 70 or even, or even greater milliseconds if you're going beyond that. Whoops. Okay, my setup slides. So next I want to talk about consistency. So this is the second concept I want to cover here. In the distributed database category, our competitors generally offer strong consistency or eventual consistency, or maybe strong and bounded staleness. Cosmos, you have 5 consistency levels to choose from. We have strong, which is basically linearized writes within your application. Bounded staleness, what that means is that your reads are going to lag behind your writes by either some number of updates or writes to the database or a period of time, some interval of time. Session, level consistency, so this provides monotonic reads, monotonic writes. Consistent prefix, so you'll get updates at a relaxed level of consistency, but all the updates you're going to get will be in order. And then eventual consistency, which, as the name implies, you will eventually be consistent, but also there's no guarantee of the order in which those updates will happen. So you could write 5, 6, 7, and then on a replica you may see 5, 7, 6. So lots of choice there in terms of the consistency levels you can set, and these are set at the account level by default. However, within your application, you can actually go and relax that level of consistency either at a session level, so when you instantiate your SDK client, or even at the request level. So let's just say you want to blast in a whole bunch of data. You don't really need it to be strongly consistent or any strong level of consistency, but you want to improve the performance of that, like we showed earlier with PACELC, right? Relax consistency, reduce latency. So you can reduce that consistency level, get much better performance, and then just drop that connection or drop or let it go back up to the default there. Also, another thing I want to point out is for all the consistency levels, the reads are guaranteed at 10 millisecond and 5 nines availability. So an important point to keep in mind there. Another thing I want to point out too is with respect to latency versus consistency, there's actually a direct relationship between these things. And in fact, the impact of that is more pronounced with greater distance. There's not many things in computer science that touch on things like the speed of light, but when you're dealing with a distributed application that's having to replicate and communicate over hundreds or thousands of miles, the speed of light actually becomes a factor with respect to the latency within your application. Packets can't travel any faster than the speed of light, of course, and within many WANs, they're going to travel a lot slower, right? Every packet has to go through numbers of routers and optical switches and all kinds of other crazy equipment. You could have lossy links and other things impacting the performance of your network. So each of these things will impact the performance of your application or the performance of that latency within an application when you're replicating between lots of nodes over a great amount of distance. One thing I want to point out too is recently we enabled customers to be able to enable strong consistency across regions. Now, when we talk about the latency versus the consistency, you obviously are going to have a trade-off there with that latency when you're replicating across great regions. So one thing to keep in mind is the greater the distance in there, the greater your latency is going to be. One other concept I want to talk about too is the consistency level you choose also has an impact on your throughput. So in Cosmos DB, for strong level of consistency, your writes are going to be a global majority, right? So if I'm replicating in multiple regions and I have strong consistency set for that account, I need to commit to every region I'm replicating to, ACK it, and then return it back to the client, right? If I'm using a relaxed level of consistency, I'm going to do a local minority. So that means, and you saw in Andrew's slides earlier, when we talk about a replica set, there's 4 replicas within it. You've got a leader, a couple of followers, and then another, oh, that's wrong. That should be a forwarder, not a leader up there on the top. So with quorum writes, for anything but strong, you're going to write to 2 of those, a local minority within the replica set. On reads, for strong and bounded staleness, you're going to read, whoops, what happened to my, well, all right, I missed my animation here. Local majority, you're going to read from 3 of those within there, right? It has to be a majority of the replicas within the set. And then for relaxed level of consistency, so session, consistent prefix, and eventual, you're just going to read from a single replica within there. All right, so let's show you some demos. So let me set this one up. I've got about 5 demos in this one and a bunch of different scenarios, or 2 demos and a bunch of scenarios. So this one here, I'm going to show you consistency versus latency. So I have an account with eventual consistency, and I'm replicating from West US to Central US, about 1,000 miles difference between these 2. Next, I'm going to show you consistency versus latency with an account using strong consistency, replicating over that same 1,000 miles. And then third, I'm going to show you an account with strong consistency, but now I'm replicating at twice the distance, roughly twice the distance in there. After that, I want to show you consistency versus throughput. So I'll show you one example of what your throughput is going to be when using eventual consistency, and then what it's going to look like if you're using strong consistency. All right. You guys like demos? Is that okay? Is there too many demos in this talk? No? Okay, just checking. Okay, I'm going to test 100 writes in West US, eventual consistency level, and my replica is 1,000 miles away. Anybody want to take a guess as to what my latency is going to be? Is it going to be slow or fast? Let's see. Blazing fast, roughly 6 millisecond per write. Okay, now I'm going to test 100 writes in West US, strong consistency level, my replica is 1,000 miles away. So what's going to happen? I'm going to write it in West US, I'm going to replicate it 1,000 miles away, commit it, and act back. Much slower. Not that big, less than a K. Average latency, 62 milliseconds, okay? Now, third test. Do 100 writes, strong consistency, my replica is 2,000 miles away. Who thinks, just give me a guess, what do you think it's going to be? Same? Less? Double the distance, double the latency, right? To calculate what your latency is going to be when using strong consistency in a distributed system, you only need to calculate that latency to the region that's the furthest away. So it's the round trip time from where you wrote to where you replicate that furthest region, plus 10 millisecond for the commit within the region itself. All right, whoops. Now, I'm going to do 100 reads. So this is testing throughput. I'm going to do 100 reads, eventual consistency in an account. So this is going to read from a single replica. And my average request units is just one, right? Because I'm reading, it's one compute operation that's happening, right? Now, I'm going to test 100 reads strong consistency in West US. So these are local minority reads, right? I'm going to read from 2 replicas, which is actually 2 pieces of compute, right? Every replica within a replica set has its own piece of compute. So I have 2 compute operations, and just to make this clear, the reason we do that, that's how you guarantee consistency, right, within the application, right? I'm taking a quorum, right? Is it replicated? Is it committed? And my average RU is 2, right? Because I'm doing 2 read operations against 2 replicas, right? Now, what happens if they don't agree, right? What we're going to do actually within Cosmos is look at the LSN for the write within there, and whichever one's higher is the winner within there, right? Because it was the most recent write, the most recent update within your replica set. Okay? So there's your test results there. So average latency. Stronger the consistency, the higher your latency, right? PACELC, that's the actual, those are the trade-offs. This is what this really looks like when you make a decision and choose, what do I care about? Do I care about latency or do I care about consistency? Whoops. Okay. Let's go back to slides. All right, third concept, availability. So anybody that's designed applications for Azure, particularly ones that run in multiple regions, are familiar with something that looks like this, right? An architectural diagram, right? I've got clients out there in the internet. They could be devices, phones, browsers, whatever, connecting over the internet. If I'm replicated or deployed into multiple regions, I'm going to use DNS load balancing, like a traffic manager within there, to redirect my request to the closest region to them, right? Because I want to keep that latency low for them. I'm then going to have my application deployed into multiple regions. I'm going to use a reverse proxy or a WAF in front of that, in front of the front end of the application to handle load balancing at the front end and SSL termination. And then with each of the logical tiers, I need, so I'm going to have resiliency in terms of regional, but within region, I need resiliency as well, right? When you're obviously building and deploying for the cloud, you're using commodity hardware, instances can fail, issues can happen. So I want multiples of those things as well. So I'm going to have multiple compute instances in there. I'm going to load balance within those. If any goes down, I'll take it out of the pool. replace it. So you're going to have resiliency at a regional level in case of a regional event, and then within region, right, at an individual component level. For Cosmos, you are going to have both those things. So obviously for each of these regions you're deployed in, you want a replica backing up each of those applications, the front tier and the middle tier within there. Now within region, as I described earlier, we have 4 copies of your data run within a partition set. So we have resiliency at that level. And then of course, when you're deployed into multiple regions, you've now got resiliency at a regional level in case of a regional event occurring within there. So who's seen this concept before? RPO, RTO. Yeah? Okay, so when you're designing for a distributed system, you know, high availability is just part of the task. You need to design a business continuity plan, you know, to say what's going to happen in case of disaster. And to do this, you need to understand the tolerance for your system and your business in case that occurs. So what is your tolerance for data loss? How much data can I lose? Or how long can I be down for, right? So in this scenario here, or the way I've illustrated it, this is a function of time, right? My recovery point objective is expressed as a period of time. How many minutes of data can I lose should an event occur? And then in terms of RTO is also functions of a value of time, is how long can I tolerate being down for? So these are obviously driven by business objectives, right? If you're a retail outlet and it's Black Friday, what's your tolerance for downtime, right? It's probably close to 0, right? You're going to lose tens or hundreds of thousands of dollars a minute or an hour, right? That's your whole season right there. So your tolerance for RTO is really 0 versus RPO. So how much data can I tolerate losing within there? So these are critical to understand when you're designing a distributed system. So we published, this is a table we published that's out in our docs that describes the RPO, RTO for Cosmos DB using various modes, so single or multi-master, and then across various consistency levels, and then whether you're deployed into a single region or multiple regions. So for a single region deployment, your RPO is going to be about 4 hours in there. But what I really want to call out is your RTO is going to be something less than a week. So if you're building a or mission critical application, who wants to deploy in a single region, right? You would never do such a thing, right? You have to deploy into multiple regions to provide that level of availability should a disaster or some kind of event occur that's going to impact a region. For single master mode, within multiple regions there, using a relaxed level of consistency, you're going to have an RPO of less than 15 minutes and your RTO less than 15 minutes. If you're using automatic failover, and that's using automatic failover for that RTO there. If you're using a manual failover and you detect that even quicker, you could failover as quickly as you want. But we guarantee within 15 minutes from once we detect that the region is no longer available. For bounded staleness, you're at a single master multiple region, you're at about 100K updates or about 5 minutes for RPO on the same RTO. And then for strong, of course, your RPO is going to be 0, right? Because I've replicated to another region. So if that event, or excuse me, if that region goes down, I'm safe, right? But I had to trade off something for that, didn't I? The latency. And then RTO, 15 minutes. Where things really get interesting and exciting is when you're using multi-master, right? For a relaxed level of consistency, for everything but strong, RTO of 0, right? And why is that, right? Well, what we're doing is within our SDK client, if we detect a region has gone down, we'll redirect your request and retry it in the next closest region, wherever your application or your database is deployed. So RTO of 0 within there. And then, of course, if you're strong consistency, your RPO of 0. All right. Now, you may wonder, why not RPO of 0 and RTO of 0? Anybody want to take a guess as to why? Come on, yell it out. I may give you a pair of socks later. Sorry? Right. So what does CAP theorem say? Right? Let's go back to this. So network goes down, I have a partition. I have to choose between availability and consistency, right? Another way of looking at this is RPO equals what? It's consistency, right? Remember? Go back to, whoops, I lost my other thing. I was going to put that RPO, RTO up thing, but RPO is consistency, right? When I'm choosing strong consistency, RPO 0, right? And in multi-master, when I'm choosing availability, RTO 0, right? I can't do both. CAP theorem says that's impossible, physically impossible. So that's it for this section right here. I want to transition this over to Terry, and he's going to talk about security and a pretty cool token broker that he's developed. So it's all yours.
Thank you, Mark. So I am from Citrix. I'm an architect, and not everyone may already be familiar with Citrix. So I just want to take a little bit of time and quickly go over what we do. So Citrix is mostly known for its apps and desktops virtualization. More recently, we're also known for our networking and our SaaS-style solutions. So in particular, we have something called Citrix Cloud. It's a platform that our customers can use in order to manage all of their SaaS solutions. I'm an architect within the Citrix Endpoint Management Group. It's one of our products. It allows you to manage your devices with like mobile device management, MDM, and so forth. But what I really wanted to talk about today is some of the stuff that we're doing here with Cosmos DB, and in particular regarding our journey to multi-tenancy. So we sat back and we decided and asked ourselves, hey, what are some of the most important things that we wanted to consider, right? And these were some of the ones. In particular, tenant isolation is absolutely huge for us. And you heard from Andrew on some of the trade-offs. What we did mostly with our stuff is that we're developing more and more microservices. And so we find that partition key tenancy, in other words, a partition per tenant, works out really well for us. There's a couple benefits, mostly because our microservices are quite small. And the other one is it still allows us to do those reports and those cross-tenant queries when we need to. Another thing that's super important is the concept of least privilege, right? What you don't have, you can't lose. And in particular, what I want to show in the next couple of slides is a concept that we call the token broker concept that really aids you in adding extra security and isolation between your tenants. And finally, high availability. So Mark talked a lot about why that's important and how to do it. And in fact, I had never met Mark before, like 2 weeks ago or something like that. And the architecture that we have actually resembles a lot of what Mark showed, with a traffic broker and an app gateway per region and so forth, right? So these are patterns that you do see in the industry. And certainly, when you think of high availability, it's nice to add it and whatnot, but there's that cost when you go cross-region. We're a global company, and we set up a front end in Northern Europe, and we were seeing 500 millisecond round trip times. And that is absolutely noticeable to your end users in something like an admin console UI or something like that. So when they released multi-master, we jumped on that, and we haven't looked back since. I mean, our round trip times went down to 125 milliseconds with all of our additional stuff. And that's just been such an improvement, and that is absolutely acceptable in terms of UI responsiveness and so forth. So I'm going to talk now about that token broker concept. And at a high level, what it means is that the service that is connecting to your database doesn't actually have any inherent permissions to that database. In particular, it doesn't have the master key. And that's kind of huge. With the master key, I mean, that's it. It's game over. If you lose that, you can do whatever you want to the Cosmos DB, right? So what I'm not showing here is the authentication part, but it's assumed that you have your client that's already been authenticated, maybe to some kind of front-end authentication service. Maybe it's federated to even your customer's Active Directory environment, whatever it is. The expectation is you end up ideally with something like a JSON web token or an OAuth, something that gives you a set of claims. And what you typically expect to see in those kind of claims are the tenant identity and probably the user's identity. In fact, if you're writing a multi-tenant solution and you don't know the tenant's context at all times in your processing, that's pretty worrisome, right? So these are pretty much table stakes when you have a multi-tenant service. So in this case, I'm going to start out with the client has already authenticated. It's got something like a JSON web token with these claims. And these claims obviously go to your service, and it does the validation of these claims. And now we've authenticated, and everything looks good. But the service now needs to either write or read from that Cosmos DB, but it doesn't have any access on its own. So what it does is it adds the database query that it wants to do, and it sends both of those over to a helper service that we call the token broker service. And that's the only one as mentioned that has the master key. Now in practice, the master key is probably in something like Azure Key Vault. It's up to you how you want to secure that. It's certainly in memory though. Now the token broker service, what we recommend is it has to revalidate those claims. And that's because of that least privilege concept. What if that service was compromised? You don't want to necessarily trust that service. So the due diligence here is to revalidate those claims. And honestly, if you're using something like JSON Web Token or something similar, that's usually pretty fast. You can be done in memory, for instance. So now that you have, you've revalidated those claims, and what you can do is you can take that tenant claim and you can compare that to the DB query, and you can see if that tenant is allowed to make that DB query. Now, as mentioned, we are doing partition key isolation for the most part per tenant, and so it's quite easy. If tenant Acme is trying to make a DB query that goes to partition Fabricam, that's a no-go. That's an obvious cross-tenant query. You can also do this at the collection level if you decided to do collection level tenant isolation. But however you do it, it makes it really simple to see if that query is trying to manipulate someone else's tenant's data. Assuming that the tenant is making a query that they're allowed to make, it generates what I call an access hash. And I'm going to get into that. There's actually two different things that Cosmos DB allows you as a set of data that you can use to authenticate. And that gets sent back to your originating service, which then uses that to finally make the request to Cosmos DB and so forth. So what I'm going to cover now are those two different types of access hashes. Now, everyone is familiar with a master key, but that's not actually what goes over the wire when you authenticate to Cosmos DB. That would be bad. Underneath the hood, what actually happens, and this is well documented, is it generates an access signature that basically is a hash of your request using the master key. And that is what I call the master key signature. And that, in turn, is what, as mentioned, goes over the wire. It's actually one part of the authorization header. There's some other stuff in there that make up the full authorization header. Now let's talk about resource tokens. Not everyone is familiar with resource tokens, but it is well supported in all of the various different API interfaces to Cosmos DB. And underneath the hood, what actually happens is Cosmos is creating a user, a special user, with a set of permissions. It's basically like a delegated master key. And even though this isn't documented at all on Microsoft's documentation, underneath the hood, they actually are generating a resource token signature, and that's what gets sent over the wire, right? So now let's talk about what you can actually use and send back from your token broker service. You don't want to send back the master key. That's the whole point. The master key signature, on the other hand, is great. Very delegated, tight restrictions, and I'll talk about the features of that. The resource token is also meant to be something that you can send over the wire to another service. The resource token signature is not documented on purpose, to be fair, right? It's more of a black box, and unless you really want to reverse engineer that, I don't recommend sending that. You could send the authorization header, but the SQL interfaces don't really provide good support for interacting with authorization headers. So it's kind of recommended that you send back the resource token, which as mentioned has good support, or send back the master key signature if that's the part that you're using. Now let's talk about the differences between the two and the pros and cons between the two, because there's some some key things here that you got to be careful about. The master key signature is super fast to generate. It's just a hash. It's all done in memory. It's only valid for a few minutes, which is actually a good thing. And it's very specific to the operation that you want it to do. If you were trying to edit, it's going to only let you edit. It's not going to allow you to create or delete or anything like that. Again, that's really useful if you're trying to do like a least privilege principle. But this is the killer, and this is very unfortunate. It doesn't encode the partition key that it was targeting. And so if you have a master key signature, it can be used for any partition key. And if you're doing isolation on a per partition basis like we are, that was a no-go for us. If you're doing it on a collection basis, however, this is great. So let's talk about resource tokens now, and this is actually what we ended up using. The downside with a resource token is you can't generate it yourself. The resource token has to go to the Cosmos DB. And then, so you have that round trip time, the access time. As mentioned, underneath the hood, it's actually creating a user, creating some permissions, and so forth. It's got a very flexible expiration time. The default's 4 hours, but you can have it up to a day. And that does lend itself to some nice things. You can cache these resource tokens. Some trades, some downsides. The longer you cache it, the longer your expiration, the longer the damage a malicious person could do with it. But still, it makes it really convenient, and it also reduces the downside, which is that round trip time to go get it. And the scoping is either read or all. You don't get that super fine level granularity that you did with master key signature. So I'm going to show you now the latency, a demo of what this means in practice. And in particular, what I'm going to show you is the latency between your front-end service when it makes a call to the token broker, and then you get back that access hash. And that's either the master key signature or it's the resource token. So I'm going to switch now to my laptop. In the top here, it's not very obvious, but in the top here is my token broker, and I'm actually doing remote logging. I'm actually looking at the logs for a little web app for container I have. Apparently for the last 15 minutes, there's been no traces. On the bottom one is my configuration service, my front-end service that actually is the one making those database requests to the Cosmos DB. And then I'm just going to use Postman to simulate a client request. And I'm going to start with a resource token. And I'm going to make some requests, and I'm going to make a couple of them just so that we can see averages. And you can see that I am getting back some tenant information. Now I'm not seeing any traces. So what I'm going to do is I'm going to terminate this. I think it was just a little bit too long. And we're going to connect back and do that remote logging. Yeah, in fact, you can see the trace messages there that weren't being shown up earlier. So let's wait for the top one here. And you can see that round trip time from your token broker service to the Cosmos DB to generate a resource token is taking around 55 to 60 milliseconds or something like that, right? Now, that is control plane. It does, Cosmos DB is doing some work there, which is why you see that, those double-digit numbers. And then from your consuming service, that's typically around 150 milliseconds or so, assuming that they're in the same, closely located, right? So basically, it's an extra latency of 150 milliseconds to get that really nice tenant isolation, and to basically to remove the possibility of SQL-style injection attacks, which can absolutely happen with something like a NoSQL solution, such as Cosmos DB. So that's been very acceptable for us, and again, this is without caching. And honestly, it's without any optimization whatsoever. Now let's go to master key signatures. So I'm going to make this request a couple times again. And it is so fast that it's showing up as 0 milliseconds, right? And again, all that it's doing is it's just hashing the request in a specific way that works and is understood by Cosmos DB. So this is, as mentioned, by far the superior solution if you're not doing partition key isolation. And then if we look at the total round trip time, the total extra latency from the point of view of the service that's actually making those writes on the customer's behalf, it's around about 50 milliseconds or so, which is really nice. So that kind of concludes the concept of the token broker, architecture pattern, and how we applied what you learned from Andrew and Mark in practice at Citrix, in particular in the endpoint management group. Thanks. Pass it back now.
Okay, so I guess some session takeaways. We just want to make sure you guys kind of walk away with, what we want you to understand around here. So I just want to do some polling. So after listening to our talk, who understands kind of better the performance isolation versus cost? when building multi-tenant systems? Yes? Awesome. How about the trade-offs for consistency, availability, latency, the CAP theorem, PACELC stuff? Show of hands, yeah? You guys feel confident in that? And then on the security isolation and kind of the token broker pattern, show of hands, you guys, you have a good grasp of that? Okay, so 5s across the board then? Yes? All the way across? Yay, yes. So,
Thank you, guys.
anyway, hey, so just some resources here. So all the demos I showed, available on GitHub. So if you want to take a snapshot of that, go right ahead. Go ahead and download this. There's actually a couple other demos in there too. I'll show you, I have a test in there that shows conflict resolution for doing multi-master. So that'll show last writer wins as well as how to use a merge procedure within there. There's also another little fun one where I can show you custom synchronization to help kind of cheat speed of light. And then also Terry's Citrix, his token broker project within here that he showed as well. So help you get from 0 to 100 on implementing that as a pattern within your application. So we'll take some questions while we've got like 30 seconds. But thank you very much.